Turner, who is going to make me even smarter about 3D and OpenGL and stuff.
Thank you. No, don't applaud yet. First, let me say I'm glad you're all here and awake, because it is the last session, and I'm aware that there is beer in the immediate future, so therefore you might be more focused on the beer than you are on learning more about 3D or OpenGL renderers and things. Shh! Everybody in this room is valuable in the comments apart from that guy at the back and that guy at the front. Everyone in between, fine. Those two guys, ignore. I've got two hecklers, not even one. What did I do to deserve this? Shh! I am very charming. Hello, I'm Charming James Turner. We didn't put my nickname on the thing. I work for KDAB. We do OpenGL trainings, which we did a bit of on Monday. Were anyone who's in the OpenGL training? Okay, some of you. Good. This is going to be good for you. If you don't know anything about OpenGL, like that heckler at the back, as he told me at the coffee break this morning, bits of this are not going to make much sense. I'm going to explain some of the concepts, but if you really don't know any OpenGL concepts at all, this might be pretty meaningless in places. I'm sorry about that, but this is we can't start from the beginning with this kind of material. We assume some knowledge of contexts and OpenGL and how you submit primitives and so forth. So what are we going to talk about? We're going to talk about integrating QtQuick 2. I should probably have put that, but yes, QtQuick 2, and different 3D rendering engines, scene graphs, approaches, libraries, something other than QtQuick, which also wants to do 3D rendering, which is a fairly common problem. We see this pretty frequently, that you have some existing library that renders something scientific or medical or business-specific or industry-specific, and you want to put a nice new QtQuick GUI on top of it, around it, interacting with it. So what are we going to look at? First of all, we need to start by understanding in quite a bit of detail how the QtQuick 2 rendering model works and was designed. First of all, who's using QtQuick 2 already? Good. Who's looked at the implementation of it? Okay. More hands up. Let's see, that was 10 people, maybe 8. Okay. Of those people, did all the code make complete, perfect sense? Right. Good. So we're going to talk quite a little bit about why the QtQuick internals are arranged the way they are, and the layering, and some of the guarantees and restrictions those things bring in, and therefore what we need to do to interact with it from some other code. We're going to quickly talk about the different ways your other code might work. So that's these different scene rendering models. Something very simple, it might just be you have your own OpenGL code and it draws a triangle or a rectangle or a few rectangles. Fine. It might draw using some custom OpenGL code, like our KDAB demo of the skull that Sean here wrote. That's his own OpenGL code sitting next to QML. It might be VTK. That's commonly used by several of our clients to do scientific visualization. It might be OpenSceneGraph. That's used by another of our clients to do oil and gas visualization. It might be a different rendering library or package I haven't mentioned or talked about. Hopefully it has some similar characteristics to the ones I'm going to talk about. If it has completely different characteristics, then we need to have a proper conversation afterwards, and that will be interesting, because I'm trying to kind of survey what the different rendering engines out there need and give and want in terms of how they interact with the rest of the world. It varies considerably. Once we've done that, we're going to talk about the different ways we can make the two things interact. And the first way is to put Qt in control of what's happening. And the second way is to have Qt not be in control, to be somehow subservient to another rendering engine. And then the final option is power sharing, where they're sort of both in control, but neither really are, but both think they are, which is, and there's some, I could make a political analogy here, but I'm not going to, about power sharing and who's in control, but it would get too difficult. So first of all, we talk about what QtQuick 2 does. Hopefully you all know QtQuick 2 starts out from QML on the disk, and it builds a tree which basically corresponds one-to-one in memory of QtQuick items, so things that inherit from QtQuick item. And there's basically a subclass for each item you see in QML. There's a rectangle and an image, and a list view, and a text element, and so on and so on. Each of those corresponds to a subclass of QtQuick item. Fantastic. And they've got methods you would know and expect. They have properties, and the properties exposed to QML, and they have event handling, and behaviors for focus and accessibility, and so forth. And none of that's to do with rendering. The rendering is done by a layer called the scene graph. And this is just a folder. If you go and look at the source code, there's a folder called scene graph inside QtDeclarative/QtQuick/scene graph. And it builds a completely parallel tree of things which are called QSG nodes, so Q scene graph nodes. And this is what does the rendering. So there's a phase update paint node where the QtQuick item, whether it be a rectangle or a border image or an editable text or a list view, can create one or probably several, if it's a list view, lots of SG nodes which somehow display itself on the screen. And there's a threading synchronization boundary here, which we will talk about in a little more detail. So this is our QML tree is built on one thread and on one side, and then we build up this parallel tree when we need to do rendering. And again, it's only built up when it needs to be built up. If you're hiding a piece of content, you know it's not been loaded, this tree isn't built. If it's hidden again, this scene graph tree can be torn down. It's purely about display. What has this tree got? It's much simpler than the QtQuick items. It has transformation nodes. It supports materials, which basically means OpenGL shader programs. Yeah, the word material and shader are used interchangeably in the code. I think shader would have been clearer, but material is what Gunnar chose, so that's fine. It still means the same thing. You can have geometry, which has textures. Geometry really here means collections of triangles, because this is OpenGL we're talking about. Often it's just a rectangle, so 2 triangles, but it could be arbitrary splines and paths. There's support for clipping and masking, so mask out areas of images, either regular rectangular shapes or more complex shapes. And there's support for custom nodes, with some limitations we're going to come back to. But this is a much simpler list. This is basically it than all the different QtQuick item subclasses that exist and can be assembled. So that's what gets built by this synchronization phase update paint nodes. And if you create your own QtQuick items, which you can do, that's a supported public API, this is what you have to work with in your custom versions, which we often do for clients to, make a fancier QtQuick item for them. And then we come to the rendering model. First of all, we're going to talk about the non-threaded case, which is simple-ish. All your QtQuick stuff happens in a QtQuick window. QtQuick window is a subclass of QWindow, and it requests OpenGL support. And then there's some pieces that create for you a QOpenGL context, which is the context class we have in Qt 5. So when you use a QtQuick window, you are definitely using OpenGL. There is no way to use QtQuick 2 and not be using OpenGL. It's actually possible that could be added, but it's not deemed to be a useful feature at this point. So QtQuick window, OpenGL context is created. And that context has some particular features. For example, supporting those clipping operations requires that it have stencil support. If it doesn't have stencil support, clipping wouldn't work, and we couldn't clip to arbitrary non-rectangular regions. So stencils are required, so is the depth buffer. So this isn't just any OpenGL context, which is going to become an issue. It's an OpenGL context that has to have some certain features and configuration, or things won't work. And then, essentially the rendering phase is that we run over our QtQuick item tree, building up our paint nodes, our SG nodes, from the QtQuick item's current state. We do a traversal called polishing, which just, again, can synchronize the QtQuick items with whatever scene graph nodes they built. And then we run over these paint nodes, which we've got a big tree of, and we assemble them into batches, which isn't worth talking about too much detail, and essentially we submit them. In other words, we make drawing calls. So the transform ones end up making matrices, the materials end up activating shaders, and the geometry ones end up drawing a number of triangles. The clipping ones do something more complex we're going to ignore for now, it's a detail. So that's not too complicated. Have one tree, build another tree, traverse it, build some batches, render it. The much more common case is threaded rendering. And this is a situation that's, I mean, all of everything I'm talking about today is evolving. And one of the things that's evolving is the threading model. So this whole system was designed to allow threaded rendering, so the rendering thread can always achieve a hard 60 frames per second rendering target. This is one of the big headline features of QtQuick 2 is this threaded rendering and this fast rendering. It's an OpenGL and it can happen independent of your main thread. And with 5.0, only certain platforms were using threaded rendering. With 5.1 and going forwards, many more platforms are using threaded rendering by default. You can control this. There's both an environment variable and a command line switch, and a few other places you can get in and select threaded rendering on or off. But increasingly on, I think, all the major platforms, the desktop platforms, and most embedded platforms, the rendering will be threaded. The key decision is if your QPA plugin says yes or no to supports the multi-threaded OpenGL flag, which is just one of the flags it returns from its features list. So on embedded targets, it can vary a lot. There's ifs on Broadcoms and Raspberry Pis and XCB embeddeds, but increasingly it's going to be threaded. Was that a question there? Or just, sorry. So the rendering is probably threaded. And this means that the rendering never waits on the GUI thread. There's a separate rendering thread. It doesn't wait on the GUI, and occasionally the GUI sends custom events which cause the synchronization to happen. So state synchronization is very fast, and we've already built these SG nodes up on the main thread. The synchronization simply copies over. You have a rectangle with a color and a width and a height. The synchronization simply copies the width or the height or the color into the SG nodes on the render thread, and then that's done. And that synchronization phase doesn't make any OpenGL calls. So there's no OpenGL calls happen while the threads are synchronizing. It's just a very quick memory copying of doubles and floats and maybe some images across. And then the threads stop the synchronization phase, and the rendering thread goes back to rendering as fast as possible. And apart from that, what I said before doesn't really change. But because the threaded rendering is optional, there's no accessor on QtQuick window to say, give me the rendering thread. It might not exist, or it might. There's no accessor to say, stop it, or pause it, or put a mutex on it, or in any way control the synchronization of it. It's got to be left untouched, if it exists, to run at 60 FPS. So suddenly you've got this problem that there's a box that might be here, and it might be doing all your OpenGL somewhere you can't really get at. And that's what we need to work with and integrate with if we want to keep QtQuick rendering quickly, but use some other OpenGL. So the good thing is we now have a fairly straightforward way to do a basic integration. And this is what is a good starting point for integrations if you're starting from clean code. QtQuick window provides some hooks before rendering and after rendering, and these are signals. And these get called, as you might imagine, before it does the rendering phase, so before it sends OpenGL commands, and after the rendering phase, after it's done all its OpenGL commands. Hooray. And you can use these to make arbitrary OpenGL calls before the SG node tree is rendered. When these get emitted is up to the rendering thread. And again, there's different thread and render loop implementations depending on the animation system and Windows and Linux and so forth. But there is a rendering thread happening, and it will emit these signals at some times it decides, probably close to 60 FPS if it can achieve that. And these signals are emitted from the thread that's doing the rendering. So if you're in non-threaded mode, it'll be the main thread. But if you're in threaded mode, it'll be the actual rendering thread if it exists. So this means you can connect to these signals, inject your own OpenGL code, render it, and it will appear underneath the scene or on top of it. And you get the context that QtQuick window made you, which has that depth and tensor support. There are some issues. By default, obviously the QtQuick scene clears out the existing drawing surface before it starts rendering. But if you've drawn something underneath, it would then clear it and you wouldn't see it. So you have to switch that feature off. There's a set clear before rendering, true or false, on QtQuick window. Great. The next problem then is that all the OpenGL stuff, the textures and scene graph nodes and the frame buffers and the VBOs, has some overhead. And if you can't see that particular tab or section or view or WebKit instance, we don't want to have them hanging around. That would be expensive and it would waste GPU memory that on better platforms might be very scarce. So the OpenGL context and all the scene graph stuff is not what's called persistent. If it doesn't need to be drawn, it all gets torn down. Or if there's a low memory situation, it all gets torn down. Or if there's some resource scarcity for some other reason, it can all get torn down. And then when it needs to, it'll all get created again. So there's not a one-to-one lifetime correspondence between your QtQuick window and your QtQuick items and all your scene graph stuff. They might bounce in and out of existence several times without you really knowing about it. That might be okay for you, but it might not. So there's another flag which says, don't do all that stuff, make the OpenGL context persistent. Once the QtQuick window is created and shown, you'll get one OpenGL context and it'll stay around until the QtQuick window is destroyed. So that's worth often trips people up. The next problem is that these before rendering and after rendering things are signals. And they might be coming from a different thread. And you all know what happens with cross-thread signals in Qt, right? What happens?
Depends on connection mode. You have auto connection, sends asynchronous
Right.
queue, event queue, and
Yeah.
direct.
Yeah. So if you don't request anything default, the default connection mode for signals and slots between different threads is that the slot is run in the receiving thread context, which usually will mean the GUI thread. But because they're not synchronized, the rendering thread will be off doing the rest of its rendering, and it won't have waited for you to do your OpenGL rendering, and it's not going to work, and it'll probably crash because you'll try and access OpenGL state from the wrong thread, and terrible things will happen. So you need to connect to these signals directly. So the fifth argument that you normally ignore needs to be Qt direct connection. I haven't actually tried leaving it out, but depending on how forgiving your drivers are, it's going to go wrong sooner or later. So that's a problem. And then finally, two finallys. Yeah, double finally. Once you've done some OpenGL drawing, QtQuick is going to use the context to do the rest of its drawing. And if you've messed up textures or VBOs or vertex arrays or anything like that and put them in a funny situation, or maybe you've enabled alpha blending or disabled depth testing, if they aren't how it expects, its rendering will go wrong, often to do with clipping or text rendering or anything else. So you have to make sure you put the OpenGL state back to what QtQuick expects. Fortunately, in 5.2, there is a brand new helper added by Gunnar because we asked him nicely. And essentially, it's a put all your state back the way I need it so I can draw correctly without errors. And I've forgotten the name of it, but it's something sensible like reset OpenGL state. There you go. It does what it says on the tin. But if you forget it and you mess up the state, things will go wrong. But there's a final issue. So the OpenGL context we're using was created by inside QtQuick window, and we don't have much control over it at this level. So therefore, its surface format was created by QtQuick window, and therefore its OpenGL profile, core or compatibility, its OpenGL version, and all its buffer size settings, stenciling, stereo, all those features we can't control. And at the moment, QtQuick selects a compatibility profile, and that means on Mac it selects version 2.1. because there is nothing higher than 2.1 on Mac that isn't core. Hello?
You can control it. You can call set format on the QtQuick window, and it will use the format you pass in.
But potentially go wrong.
Yeah,
Okay, right. So if you want it to work, yeah, you can control it, but it might not work. Great. We're planning to remedy this such that it will actually work with a core profile as well as a compatibility profile, because that would be very useful. So the point of these restrictions is that if you have some existing arbitrary rendering code that needs, for example, and it needs accumulation buffer or needs core mode, you might not be able to use it directly with this approach. But all those minor issues aside, that brings us to a standard demo. And I didn't even bother to write my own version of this. I just literally used the one that ships with Qt, but people often seem to be unaware of it, so I shall run it for you now. As I say, the demo that we've got on our stand does exactly the same thing. This here is some QML content. It's a round rect and some text. And underneath it is some OpenGL rendering using a shader and some triangle primitives. So in the before rendering call, this does a direct connection, does its OpenGL rendering and finishes. It doesn't do any damage to the OpenGL state. The QML renders on top. We're happy. We obviously, this had to set off disable declare before rendering, so we didn't lose the background image, and that's that. And that's extremely robust integration. Going forwards with how we expect QtQuick rendering to develop, this is going to work. But all our rendering is happening in the QtQuick thread, and we haven't got too much control over when it renders. But if it renders 60 FPS, which it should, we're happy. So, that was easy. We're done. Yeah, cool. Beer? Right. Unfortunately, we have some issues, as if you couldn't guess. The above approach works pretty well, and if it works for you, do use it. All the things I'm going to talk about from now are if it has some of the issues we're going to see here, but what we just saw is simple. The example is there, it's part of Qt, and it's going to work going forwards. As we can talk on now, it gets increasingly more likely to break with different versions because we might use some private APIs, and it might have more performance impacts, but equally might give better performance. So let's say in my QtQuick 2 items, I want to do some completely custom OpenGL. Rather than just those geometry nodes and materials, I want to do something different. What if I've got a rendering library that I want to call into in before rendering that wants to use its own OpenGL context because we can't control it? That happens quite often. What if we've got a rendering library, which is a modern high-performance scene graph, like OpenSceneGraph, that wants to control its own threading? Or what if we've got a rendering library that wants to actually run its own event loop, like app.exec does in QApplication, and control its own drawing? In all of those cases, what we just saw isn't going to fit. We haven't got a nice simple render call that we can call into and things will happen. Well, we may not do. So before we go any further with the complex things, we should briefly talk about layering. Maybe you don't need to integrate two renderers at all. Maybe you can just visually overlay them. And this often works better on embedded systems because they often have hardware support for it. Maybe you can simply have almost two distinct renderers which are visually combined on the screen using hardware overlays or potentially child windows. This, unfortunately, is totally dependent on hardware nuances and, for example, will be different on XCB versus Wayland and how composition is handled. And if it works on your embedded target, for example, if you want to show an OpenGL UI over an OpenGL map in different processors, it can work with absolutely no penalty whatsoever, or it can just not exist. The feature might not be there. But if you can simply not combine the renderers, but have them essentially be ignorant of each other, but just visually appear on top, that could work quite well. And just for a little demo of it, I've got one here to show, put this one down, just to show that this could be possible. Oh, come on. There we go, right. Ooh, that's interesting. I say. Okay, this has done something different running multi-windowed, like multi-screened, to what it does normally, which is a little ominous, to say the least. So I think I've just proved about the bugs that could happen. So this is two different windows. This is actually, has it worked down here? Yes, it has. Okay, sorry, that's OpenSceneGraph being multi-window support. Right. This here is an OpenSceneGraph window. Actually, I've got two because it's multi-display support. That's an OpenSceneGraph teapot rendering using OpenSceneGraph. And on top of it is some QML content. It's even handling mouse areas, so it turns black. Don't ask me about that texture corruption it was doing. That's a QtQuick window as a child window of the OpenSceneGraph window. So there's two separate renderers. This has its own OpenGL context, which is rendering fine. This is its own OpenGL context, which is rendering fine. Separate contexts, but they're overlaid visually. This one's event handling works. This is using the standard OpenScene graph mouse interactors. This is using the standard QtQuick event handling. Mouse tracking is working merrily, he says. Yeah, it is. Things look pretty good. And if I move this around, it works. I didn't get it working on the Mac, but it ought to be possible to make this window have an alpha channel. And then you could even see through to the OpenScene graph rendering, though that's going to need a bit of playing with hardware options and, again, driver support to have a system window support alpha blending down onto a native OpenGL window. But on some platforms, that's going to just work as well. Again, on an embedded platform, that might just work. And the great thing about this, again, is it's robust. If this approach works for you, you can simply stack child windows on top. Then, yeah, they're both separate. You can test them separately. And you can be reasonably sure when you deploy them, if you've tested that driver and hardware, it's going to do the right thing. If it doesn't, it might do any number of things. It might simply not work. But equally, there might be some hit performance penalties. The classic example is that many OpenGL context and windows are slower if there's even one pixel of another window covering them. So in this case, there's an entire child window covering many hundreds and thousands of pixels. This will always be on a slightly slower code path because there's pixels obscuring the main OpenGL window. But actually, it's still fast enough. So if it's fast enough for your application, then maybe that's a good trade-off, because as we're going to see, the other options you might employ might be significantly worse. But it's just worth emphasizing that simple is often best, and this is an example where it might do. So, returning to less simple options, where are we? Oh, I need to quit this, hang on. Okay, do we actually need to integrate the renderers? Possibly not. If we can get away with it, let's not. But it's a bit tricksy on hardware and driver issues. As a side note here about context adoption. We have this QOpenGL context, which hopefully you've all at least seen, if not used. And it's a platform abstraction around a native thing, NSGL context on Mac, although arguably NSGL context is an abstraction around CGL context, unfortunately. WGL context, GLX context, and presumably something different with Wayland. I don't know how that architecture looks on Wayland at all, but there'll be something else in there. Or EGL context. Well, Wayland can use EGL, so it may just be an EGL context again. But it's some native structure, which is opaque to us. And say we have this nice wrapper, we use Qt, we just use QOpenGL context, and we're happy. Unfortunately, there are some people out there who don't use Qt. It's weird. I'm not sure what their problem is, but they don't. They write their own abstraction layer around NSGL context and WGL context and all of these things. And so therefore you will find that, for example, on OpenScene Graph or Ogre or VTK, somewhere in their code base is a mini version of Lighthouse, a mini version of the QPA system, which can wrap up a platform window and one of these contexts in some kind of, VTK context or OSG graphics window or whatever it's called. And the problem, and usually they'll give you a void star pointer to one of these native things. But at the moment, there is no API on, dollar platform where it's whatever, any one of these, to go from one of those to a QOpenGL context. We can create one from scratch, but we can't take a context somebody else built for us, wrap it up in the QOpenGL abstraction, and then use it to pass it to, for example, QtQuick window or any of the other QOpenGL classes. There's a patch to do what this describes in Gerrit, not from me. Who's it from? Who submitted that? Yeah, someone submitted this because it's a useful thing to have, and it will make a few things a lot easier. Right now you can do it with horrible, horrible tricks, but essentially this is going to be a useful thing to have going forwards. In the absence of it, we're stuck with the configurations where we can give the context that Qt's made to our other rendering library, which cuts down our choices. So this says, it's in a bit more detail, generally speaking, most of the renderers, the big ones you might target, like VTK or OpenScene Graph or Ogre or insert renderer here, will have their own little platform abstraction layer. For example, it's graphics window in OSG, it's render window in VTK, and more besides. And often they target the native API, but sometimes they target Qt. So OpenStreamGraph has ones that target Cocoa directly, and iOS directly, and Android directly, but it also has one that targets Qt, because essentially they treat Qt like a platform to target. I think VTK does the same, actually, and because Qt's popular enough that that's worth doing. Or they target weird things like glut. And these abstraction layers, they don't just cover the OpenGL context, they cover things like mouse event delivery and keyboard focus and accessibility. Resizing, closing the window, mouse and keyboards, menu bars. And the problem is that nearly all of them are crap. They give you, they're trying to mimic glut. They give you a basic window and maybe a close box if you're lucky, and possibly a way to customize the menu bar, but usually not. But they are simple abstractions to get something running portably, but they're not good abstractions, and they're not fully featured abstractions. I mean, they don't handle all the event options and accessibility options that Qt has, because Qt's much better at doing this platform abstraction job than any of these renderers are. Unfortunately, we can't tell them all to go and use Qt for their abstraction layer. That would be much nicer, but yeah, and we'll save them time in the end too. And usually, based on the ones I see, most of their users are also using Qt as well, because if they were building a rich cross-platform 3D application using VTK or OpenStreamGraph, you also want to give it a dialog box or a file open box at some point. You're not going to go and write that by hand, so then you end up using Qt anyway, but yeah, they all do this bit themselves. So to look at a specific example, we'll look at VTK, which is one of the common ones that we see at KDAB with different clients. VTK can talk to Qt natively. Unfortunately, it uses the Qt4 API. It provides a VTK Qt render window, which uses QGL widget, the Qt4 API. Fortunately, you could fairly easily build a Qt5 variant. I didn't do this VTK yet, but it can be done. And the good thing is that VTK is a fairly simple renderer. Actually, VTK is bordering on an archaic renderer at this point. It was designed for OpenGL 1, and that still shows. But it does mean it gives you a top-level function like render on the renderer object. And inside that render function, it basically goes and synchronously does whatever rendering, whether it's an MRI scan or streamlines or polygon points around a CFD volume, whatever VTK thing you've configured, it will go and render at that point, however long it takes. And that means that this is compatible with that before rendering signal, because we can go and hook up before rendering, do a direct connection to it, inside that call VTK renderer render, and go forward. And this is straightforward because VTK itself is not threaded for rendering. VTK does use other cores for doing data loading and generating data on the CPU, but the rendering part of VTK is basically single-threaded. I'm sure someone's going to tell me that there are modes out there where VTK can do multiple threads, but the common case is single-threaded. So that seems pretty good. We could run VTK rendering under QML from that, and QtQuick from that before rendering signal. But we have some problems, because all this rendering might be happening in a separate thread. But we're talking to our VTK actors and our VTK polygon, tube extractors and all those VTK things potentially on the main thread. So, and arbitrary VTK calls, we don't really know which ones might allocate textures or make other OpenGL state calls. So we need to be rather careful to essentially look through the VTK source code and figure out which bits of API we can touch safely from the main thread versus the render thread. And that's quite awkward. And not just a question of from the correct thread, but also when, because again, we don't know. There needs to be a valid OpenGL context to make these calls, and we need to make sure we can give it one. And on the main thread, you say VTK actor move or set position, or change your streamline contouring from 0.5 to 0.6 based on the GUI slider. But if that goes and recalculates a bunch of rendering primitives, that's got to be delayed somehow until the rendering thread when it can go and update those buffers. You've also got some sort of somehow forward events into VTK, but fortunately the render window and those classes will help you do it a bit. So that's a kind of example of this is possible, but it's not trivial, and particularly you're going to end up reading through the VTK sources to see, ultimately does calling this setter cause a bunch of OpenGL state to change? I can't tell you for any given approach if it will or not until you go and look. But in principle, that's relatively straightforward with the API we have. Then we have a much more complex example, which is one that's a little bit dearer to my heart because I use OpenSceneGraph for some other projects. OpenSceneGraph is a much more modern rendering library than VTK. And therefore, it does phased rendering. The phases are called update, cull, and draw. Update runs over the tree of nodes you give OpenSceneGraph and does animations, sets things to be visible, invisible, and so forth. Culling works out what's visible in the current camera or cameras. If things are behind you or occluded, they're removed from drawing. And then finally, it goes and actually it builds up a series of what are called render bins and sends all the OpenGL commands in those bins to OpenGL. That's the draw phase. And it has configurable threading modes. It can run in single-threaded, where these all run one after the other on a single thread. It can do a thing called draw thread per context, where this runs in its own thread. And it can do things like there's actually about 10 threading modes, like a thread for each camera's culling, and then a single thread per drawing. So you might have 5 cull threads if you've got 5 cameras in the scene, and then 1 more thread for doing the actual drawing. And these are pickable at runtime, based on platform and number of cores and so forth. So you can't say when you configure your OpenSceneGraph thing, it's going to be single-threaded, or you could force it if you really had to, but normally it's picking one of these. What? Oh, there's a B in here. So, ideally, each of those phases is overlapped. So when we're doing the update for one frame, we're culling the frame before, and we're drawing the frame before that. And internally, we've got this hierarchy of nodes, OpenSceneGraph nodes, this is not QSceneGraph nodes, and they're being boiled down into things called into batches, which are called render bins, other transformations happening, and ultimately we send those vertices and textures to OpenGL. And if the render and cull threads exist, remember there might even be 6 or 7 cull threads and 1 or several render threads. If they exist, again, the public API of OpenSceneGraph hides them from you. There's no stop and pause and get me the thread handle kind of queries. And all of this strongly parallels QtQuick 2. I could also just be repeating myself. I mean, rather than saying QSceneGraph, I'm now saying OpenSceneGraph. And that's because there's only really a couple of ways to build a scene graph engine. And Gunnar's not an idiot. He followed the sensible pattern and wrote what is the standard practice for how you structure scene graphs in the modern world. So that's how OpenSceneGraph roughly works. And then we have the battle. OpenSceneGraph's world is great. It's in charge, it creates context, it schedules threads, it updates things, it culls things, renders them. QtQuick 2 also creates the threads and context and schedules things and builds scene graph nodes and renders them. And only one engine can be in charge of rendering. This is actually a lie, as we're going to see later. But for now, let's pretend only one engine can be in charge. And both the engines hide their internal threading. But if you want to share the rendering, they need to share an OpenGL context. They need to not trample each other's OpenGL state. And certainly need to be able to put it back to a sane state so they can both work. So this is just repeating what we said for VTK. The libraries which have a well-defined render entry point, you can put QtQuick 2 in charge. That's what we would do for VTK because it's single-threaded. Assuming the timing guarantees work, and assuming the other rendering code is thread-safe, which again, VTK probably isn't completely thread-safe, but you could probably make a subset of it that was useful thread-safe for a given class of problems. If it's your own renderer you've written, like Sean's thing rendering the MRI scan out there, he just knew that it would be running the rendering commands on a separate thread and allowed for it. And say we have this helper in 5.2 to reset the OpenGL state after calling this some arbitrary code. So the QtQuick 2 in control is easy, but it's definitely going to be doing all of your render work on one thread, and that's it. But that's obviously not going to work for OpenSceneGraph with its multiple threads and scheduling things at different times. So wait, rather than being stuck, I found some interesting private APIs. I was grabbing through the sources. I mean, you're all Qt developers. You all know to use the source, right? You look through the source code. You find some interesting things. One interesting thing we find is, I'm going to put my OpenGL arbitrary places in the QSceneGraph scene. There's this thing called QSG render node, which I didn't mention it on my slides at all. I showed you a list of transforms and geometry materials. Didn't mention this QSG render node. It's got a virtual method called render. And in it, I can go and make arbitrary OpenGL calls. I'll just go and, plug my rendering function into this. That'll be fantastic. Great, we're done. No, you are not done. This is a private API for a reason, and you're not going to do this. That's because in 5.2, Gunnar has rewritten the renderer, as he can do because it's private APIs. He's rewritten the renderer for very good reasons. It's now going to combine and reorder all the geometry it makes into much larger batches. Much larger means that he's making many fewer OpenGL calls, which of course means it's faster. It is up to 100 times faster. Gunnar is very happy. And everybody's happy because their QtQuick applications will run faster on their devices. It will not tolerate, in an arbitrary node, you making arbitrary calls to OpenGL. This would break his reordering, because your hierarchy might have a rectangle here using something, but it might end up compressed into a buffer with 20 other rectangles and 50 other pieces. He's really taking apart the entire scene and putting it back together, and he can't do that if somewhere in it is a little bit of custom OpenGL. That would make him very sad. So, in your custom nodes, all you can do is customize those existing node types I talked about, which are a texture, a geometry, a shader, a material, and a transform, and some clipping. So, even though this API exists, you can't use it, don't use it. So instead, we need to think what else we could do. There's some more private APIs. Actually, QtQuick 2 has a private plugin API. Lots of fun things in here. And we can supply our own renderer, which is a subclass of QSG renderer. Essentially, it gets past the entire QScene graph scene, all those SG nodes, and told to draw them. And at some point, the rendering loop for the whole QtQuick window says, OK, draw this entire QtQuick scene, and I'm going to go and draw it. And that happens from the QtQuick rendering thread according to its policies. But we can ignore it. We can put external renderer in control. And this thing also gets to create the context, by the way, or return the context, QOpenGL context, that's going to be used to build all these nodes up. In a bit more detail, we have this custom QSG renderer. We make renderer do something or nothing. And then let's say we have another renderer, like a machine graph, that has its own entry point from its thread loop, its run loop, its drawing pass, its drawing thread. We have that entry point, and we can use that to go and set up and run all our QtQuick 2 rendering using the context we've supplied. The problem is this approach is quite complicated. It's sufficiently complicated that I couldn't make a demo work in time for this talk, which is one of the embarrassing things. I was hoping to, but there's so many pieces to get in line, I just couldn't, with what I was trying, get you an actual demo of this working. I ran out of time, I'm afraid. But I guess I should give you an idea that these things can get pretty non-trivial pretty quickly. But to give you the applied example, for example, in OSG, there's this OSG graphics window. We can actually had to update it to use Qt 5 rather than Qt 4, but that was OK. We have a thing called an OSG drawable. That's just a thing that can be drawn by OSG. We have our custom renderer, and we make the draw implementation of our OSG drawable kick off all the rendering, and all that kind of batching and rendering that QtQuick is going to do. And say, I've written all the code for this, but the configuration to make it actually work is really eluding me. It's just proving so complicated. So, and partly Gunnar said, oh, that'll just work. And I think the problem is that although this plugin API exists, no one's used it in this way yet. It's designed to support this kind of operation. And if you read the code in detail, you'll say, OK, this could work great. And if it will work for your renderer, fantastic. But I think it needs a few more API hooks to make it really usable. So that's extremely complicated, but it's potentially a way to go. But I would suggest it's going to be tricky for real situations. We have another option, which is going to be hopefully more workable, because that one proved very hard to make workable. If your renderer is completely irreconcilable with QtQuick 2, it probably supports dynamic textures, uploading a texture dynamically, video, or a texture that's changing. And indeed, QtQuick 2 itself does that. So now we could see about having the renderers with separate context to keep them apart, and then they wouldn't upset each other and could render at their own time. And then we could use frame buffer objects, FBOs, and textures to move the bits of rendering back and forth. And this works pretty well, and this is something, again, we have clients doing fairly regularly. The easy way is going into QtQuick 2. You have QOpenGL frame buffer object as a helper. You create an FBO, and into it you render your stuff, your VTK scene, your OpenScene graph scene, whatever it is, at your leisure. And you can do that in separate threads. If your OpenGL driver supports threaded FBO rendering, it'll be fast, but other drivers it may not be. And then you get your texture out, and you pass to QSGeometry the texture from your FBO, and you see the contents of your custom renderer scene in QtQuick 2. Hooray. And this is such a common use case, there's an example for it, and there's a new helper in 5.2, which is an SG node tailored to doing this job called QSG frame buffer render node, or QSG frame buffer object node. Yeah, QSG frame buffer object node, which is new in 5.2. And this is absolutely the correct, robust approach to doing that custom rendering in a scene graph, is to do it in a separate context in an FBO, then just treat it as a texture in the scene graph. That will work with the new fast scheme. That sounds pretty nice. But now if you want to go the other way, which would be more useful, QtQuick window has this thing called setRenderTarget. This lets you say where QtQuick window should do its drawing. So again, we can render to an FBO. Unfortunately, we have to be careful about threading, and we have to be careful about context sharing. Because in order for the FBO to work, it has to be in a context that's shared with the scene graph one, and it has to be one that we can set safely from the when the scene graph is initialized. So that this has to be set from the render thread. We can't do this from the main thread. However, it's quite an appealing approach because we have this full decoupling. So there is no way to say, go and share the scene graph context with this one I already made. You have to do the other way around. You have to wait till QtQuick and QSceneGraph build you the context, get it, and then create your context which shares with it. Because remember, or maybe if you don't know, context sharing requires one context is past the other before you call create on QOpenGL context. And context sharing has some overhead in the driver, particularly if they're going to use these things from different threads, because it has to do some synchronization of shared textures, frame buffer memory, all those things. It's not free. So it might actually be faster to have totally unrelated frame buffers and then simply do blitting of the data. Then there will be no thread dependency between there won't be any context sharing, just two contexts. One does rendering, you blit the data out of an FBO into a texture, and you're good. And that might indeed be the only choice. Which will now show, hopefully, the end result. See what this one does. Hooray. What we have here is a spinning cube, because I'm so original and it's nearly the end of the day and that's all I felt you needed. This is an OpenGL cube, completely straightforward. What it's textured with is a QML scene that's animated, spinning round, which says hello world. So this has been rendered into an FBO using that. We're grabbing that out and doing some normal OpenGL rendering with that texture. And it's surprisingly fiddly to get it going. It's not the end of the world, but it's certainly not straightforward. Find my mouse cursor. We have this render that's doing the 3D, we'll come back to. When we initialize when we're told the scene graph is initialized, we have to go and do some work, and we have to do a viewer, which we'll see. That's what it's doing, the OpenGL rendering. Right. This is called from QtQuick window scene initialized. When it creates the OpenGL context, and it's already made it, we get the scene called. And at that point, we have to go and make an FBO, which has to live in that context. And we have to go, and then we can go set that as render target. If the FBO was made with a context that wasn't shared, it fails. If we do this before we've made the scene and the context, it fails, and many other reasons. We have to do this from this thread or it fails. So you've got a very narrow window in which you can safely make this call. And that means that we have to then wait, in my render method that's rendering my cube, we have to lazily wait until this FPO is made, and only once we've got it can we safely go and initialize our regular OpenGL classes. There's actually probably a frame or two before the cube appears, while QtQuick initializes its context and brings it up and emits that signal before this stuff will actually run and really render. Even more points. Yeah, so this context sharing makes things complicated. But having done that, it works pretty well. A bit more complication. Your legacy renderer might be using compatibility code. It might be using OpenGL 1 with vertices. QtQuick 2 currently uses compatibility, so that would just work. But soon we'll have an option to make it use a core profile compatible mode. If your renderer heavily benefits from working in core mode, it's using OpenGL 3 or 4 features, it's not going to be able to work with QtQuick 2 until we make this change on Mac, because there's no compatibility profile on Mac above for OpenGL 3. So mixing and matching the rendering code might just not work. And again, that's where having separate contexts would work, because most systems, you can create separate OpenGL contexts. One could be version 2.1, one could be version 4, and they will work separately. And you copy between them with the texture, and that will work fine. One little last point, which I've left to the end. Event handling is easier if QtQuick 2 is in control. Because as we said, the platform abstractions like graphics window and render window, VTK, and OpenSceneGraph aren't as rich as Qt's ones. But somehow, assuming you want to be able to interact with your render 3D scene and your QtQuick scene, both of them need to be getting events and mouse events in the right coordinate systems. So hopefully you can translate from Qt events, or you already have code, into your native renderer's form. But the opposite is also possible. You can map from OpenSceneGraph events into Qt ones for some set of cases. But again, if the platform abstractions are simple, that's usually fragile. There is code out there that will synthesize Q events from OpenSceneGraph ones, for example. But it breaks accessibility, it breaks text editing, it breaks touch events. It only really works for clicking on buttons and scrolling scroll bars, and that's about it. But ideally, and this example where using the child windows works great, if you arrange native windows the right way, the native routing will just work and everybody will be happy. Or hopefully, maybe you can do all your event handling in QML, as the demos we have outside the show, and just have that do all the event handling work. Right, conclusions. There are lots of combinations to be made to work. I've shown a few of them. Lots involve a compromise on one or both sides. Putting one or other renderer into single-threaded mode, for example. They can often be negligible in the real world. But, and this is probably an important but, they can impact your whole program architecture. So retrofitting this stuff might not work. Depending on your libraries you've got, you might need to go and decide all this stuff at the very front of your program design and prototype it and be sure it's going to work quickly on all your target hardware and devices, because going back and changing it might be nearly impossible. And finally, a lot of this multi-threaded stuff, remember that as soon as you're doing OpenGL for more than one thread, things can get slower in the driver, so you need to try and have one thread making all the OpenGL calls. And so even running single-threaded might seem like the slowest option, but if it means you only have one place doing the work and it's not doing synchronization internally in the driver, that might be faster. But really think about the whole program architecture, and then the options I've mentioned, and there's more besides, would then let you think about ways to combine stuff altogether. And I think that is all I'm going to say. But we probably have time for some questions.
Yep.
How much time do we have?
We have around 5 minutes for questions.
5 minutes. If you're still awake, if you just want to go and drink beer, I will understand. That's allowed. Everybody's sitting in numbed silence. There's a guy there with a question. Oh, there's two.
That's just
You're along the same projection axis. It's like...
How do you manage depth sorting when you use frame buffer sharing for OSG and?
All that I've used so far have been OSG at the back and QtQuick on front, so it hasn't been a problem. If you want to get arbitrary bits of OSG inside the QtQuick scene, you need to do it into the FBO, which is possible. I haven't got an example of doing it. If you want to get the QtQuick arbitrarily into the open scene graph scene, then you need to be back to doing the custom renderer and getting a OSG drawable that you put somewhere spatially in the scene. And then it would just be sorted like any other OSG primitive as a flat piece of stuff. Again, using the FBOs is going to probably be the most reliable option there. Render QtQuick, like I did with the cube, to an FBO. Just use it as a texture in open scene graph, and you order it just like everything else. I mean, when I started working on, even actually when I proposed this, I was assuming the rendering using the plugin would be the easiest solution. But the FBO solutions generally are proving the most robust because they give you a degree of isolation that's really helpful. They isolate you both in terms of memory, but also in terms of timing and then threading. And that isolation gets you off the hook from so many bugs and potential issues. So I think that it's strongly looking like the way to go for most scenarios.
Hello. Do you have experience integrating QtQuick into direct 3D applications?
That's the killer example of where FBOs work, because obviously you can start up a DirectX context and an OpenGL one, hopefully without them interfering with each other, and then simply you can't share the context, of course, but you can just split a texture. So there's no way, I mean, that's the ultimate extreme of these renderers will not work together. They are using different rendering APIs, but at the end of the day, they still have textures, and you can still create frame buffer and type operations. So you can always do the rendering in FBO and then blit. It's just then you're down to blitting, and if that's whole frame blitting, that's going to be problematic. This man looks like he has a point to make. Keep in mind, I have not done that. I'm not a DirectX person at all, but intuitively that's plausible.
Basically, Mikko, so that if you are working on a full 3D scene, what should these QtQuick 2 controls be? Are they mesh or what is this type of? This is not related to your talk. This is related to what is this QtQuick 2 control. So is it just a 2D plane at some depth, or what it is?
It certainly can be. Do you mean QtQuick 2 in general, or specifically the thing called QtQuick controls?
Both. You can explain, like I lack this, that what they really are.
I'm not sure I can explain that in the remaining time available. That's quite a big question to answer. Yeah, I think just come and talk to me afterwards, because that's going to be quite big. Yeah, rather than trying to discuss it here. Sorry.
So I think that any last very fast question or no?
Go drink beer, or go drink beer soon. Oh, he's got messages for you. Sorry, don't go drink beer. Listen to this man. I'll lose all my brownie points if I go and ruin his spiel.
First, thanks to James for enlightening us.